Hello everyone, my name is Abbas, and today I am excited to present to you the petrology of asteroids through the study of meteorites. Today, we are going to be understanding the mineralogical composition of different types of asteroids, how their formation processes were different, and their implications for us today. You may be wondering, what is the difference exactly between an asteroid and a meteorite? And this is something that you're going to want to know if you're going to understand this lecture. So, an asteroid is a large rocky body in space, which is in orbit around the sun, and it is part of the asteroid belt. In the asteroid belt, there's very frequently collisions between different asteroids, and that has led to a lot of different processes, which we will discuss further later on. Whereas, when you look at a meteorite, that is an asteroid or a chunk of an asteroid which collided with the Earth. And upon this collision, there is always going to be some sort of remnants. When we can observe these meteorite samples and we can pick them up and we can examine both the sample left behind and maybe even the crater which they left, we can understand so much more about their history and how they formed. So, let's look at some meteorite samples. And the first sample that we are looking at today is an ordinary chondrite. This meteorite consists of numerous small pieces ranging from 1 millimeter to 2 millimeters in size of chondrules. These are the small round to elliptical objects that you can see in this thin section and are distinctive and give the name to this type of meteorite. These contain several high temperature minerals such as olivine, pyroxene, and trace amounts of nickel and iron metal. Some contain uncrystallized glass as well. Individual chondrules probably formed from the cooling and solidification of droplets of molten silicate glass, either in the hot original solar nebula or possibly on the surface of an asteroid, where the melting and splattering caused by these meteorite impacts created large amounts of heat, allowing these silicate minerals to form into a glass and then cool into these chondrules. How exciting. Next sample we're looking at is an enstatite achondrite. This sample is a completely crystalline rock composed almost entirely of intergrown magnesium-rich pyroxene crystals, obviously enstatite, and these crystals have been strongly deformed and are intensely fractured, and even in some points pulverized or brecciated into smaller fragments. These features were probably caused by the intense shock waves generated when asteroid bodies collided together at extremely high velocities of 5 to 20 kilometers per second. It has no chondrules, and this is the difference between a chondrite and an achondrite. This achondrite has no chondrules, and it also has only one mineral. One method of chemical processing that may explain the unique characteristics of this meteorite is melting and crystallization. As a larger body of molten silicate rock cools and crystallizes, the first crystals to form have compositions that are different from the original bulk composition of the melt. If these early crystals can be separated from the melt, for example by settling in a gravitational field, they can collect together to form a rock whose chemistry and mineral composition is very different from the composition of the original melt. This is called magmatic differentiation and is often observed in terrestrial igneous rocks, especially those formed at depths of 5 to 20 kilometers below the surface. This separation can produce rocks of entirely single minerals, particularly olivine or enstatite. This is a connection that we're going to be making between the formation of asteroids and the formation of the Earth. We're going to see another connection like this when we get to the iron meteorites later on. This next sample is a polymicted eucrite, which is a highly fragmental rock, also known as a breccia. It consists of these fragments set in a matrix of finely pulverized fragments of similar rocks or minerals. This is very similar to different varieties of basalt, which is made of mostly pyroxene and plagioclase feldspar. Unlike the achondrite, the boundary and contact between the rock fragments and the matrix are clear and sharp, indicating that there's been no detectable heating, recrystallization, or other alteration since the fragments in the matrix were assembled together. The origin and history of this meteorite must be considered in two parts. First, there was a newly formed planetesimal body in the asteroid belt, which was partly or completely melted, and as soon as it was solid, it began to be bombarded by other small objects in the asteroid belt. These created impact craters and created all this fractionation and these small fragments. Previous minerals we've looked at are from the stony type, made up of mostly silicate minerals, such as pyroxene, olivine, and feldspar. But this type is a stony iron called a mesosiderite, composed largely about 75% of iron and nickel metal, while the other 25% is those silicate minerals. The mesosiderites and other stony iron meteorites are complex mixtures of these materials, and the details of their origin are poorly known and extensively debated. Many of them show evidence of two fundamental processes that have been recognized in meteorites. One is cooling from a melt, and the mechanical mixing of different components from different sources. One explanation is that there was a silicate-rich parent body with heavy bombardment from many different types of objects, including metal-rich asteroids. And the last type of meteorite that we're going to be looking at today are iron meteorites. These are thought to be the cores of asteroids that melted early in their history, and they consist mainly of iron and nickel metal with small amounts of sulfide and carbide minerals. During the decay of radioactive elements early in the history of the solar system, these asteroids melted, and the iron they contained, being dense, sank to the center to form a metallic core. This is analogous to the metallic core at the center of the Earth. Meteorites from melted asteroids are also known as differentiated meteorites, as they have experienced major chemical and physical changes solidifying from their molten state. And sometimes they have an iron core as well as concentric layers surrounded by a silicate mantle and crust, very similar to the Earth. So, iron meteorites told us a great deal about how the metallic cores of planets formed. So, now you're familiar with the types of asteroids, their mineralogical composition, and their formation history. So you might be wondering, why is this useful? Well, first of all, there could be asteroid mining processes in the near future. As you've learned, there are iron-rich asteroids with high amounts of valuable economic Earth materials. And by mining an asteroid, there could potentially be significantly less environmental damage if we can instead mine an asteroid rather than have to deal with the many environmental impacts that come with mining Earth materials. And to highlight some of the amazing projects, there was an idea to mine asteroid Psyche 16, which is a iron-rich asteroid, which we have talked about already, and this would obtain massive amounts of iron and nickel. And mining for iron and nickel on Earth has significant environmental drawbacks, and if this could be done, this would be amazing. On top of asteroid mining, there is also impact structure mining. These commercial deposits contain world-class resources. They contain really important resources such as copper, nickel, uranium, gold, and platinum group elements, and most importantly, hydrocarbons. As of today, 60 of the 208 terrestrial craters have been identified to host diverse resources, such as these hydrocarbons, metals, and construction materials. So, the potential of these craters as plausible resource contributors to the energy sector should not be ignored. One final application of this knowledge for meteorites is in research, and I'm just going to quickly touch on the carbonaceous chondrites, which have long been known to have approximately the composition of the Sun. So the new chemical data from these meteorites is continually changing our understanding about the original solar system and the Sun today. We can even use them for dating. The original age for the solar system is about 4.6 billion years old, and that has been verified by precise measurements on multiple meteorites. So, to bring it all together, today we've learned that asteroids are the rocky remnants of material left over from the formation of the solar system. They're direct descendants of the planetesimals that once saturated the system, and they preserve unaltered samples of what the planets were made from. We learned also about the different types of meteorites, how they have unique characteristics and mineralogical compositions that we can examine in thin section, and we can use those thin sections to learn about their history of differentiation, heating, cooling, and collisions between other asteroids. And of course, that all this knowledge has real-world application. I hope today that the mysteries of the asteroid belt have been unveiled to you using these hand samples of meteorites that we were able to examine today. Thank you very much.